Testing, can you hear me? All right, my video is public now. So I'm going to be learning about introductory statistics again. This time I'll be learning about linear regression. Also, my internet has been fluctuating again, so I might have some lag during the stream. Um, okay, so last chapter I was learning about the chi-square distribution. This chapter I'm going to be learning about linear regression and correlation. If it loads. Linear regression for two variables is based on a linear equation with one independent variable. The equation has the form y is equal to a plus bx, where a and b are constant numbers. The variable x is the independent variable and y is the dependent variable. Typically, you choose a value to substitute for the independent variable and then solve for the dependent variable. Following examples are linear equations. Y is equal to 3 plus 2x. Okay. The graph of a linear equation The graph of a linear equation of the form y is equal to a plus bx is a straight line. Any line that is not vertical can be described by this equation. Okay, there's just a quick review. For the linear equation, y is equal to a plus bx, b is the slope, a is the y-intercept. From algebra, recall that the slope is a number that describes the steepness of a line. The y-intercept is the y-coordinate of the point a 0a. The line crosses the y-axis. Okay. Before we take up the discussion of linear regression and correlation, we need to examine a way to display relation between two variables x and y. The most common and easiest way is a scatter plot. Following example illustrates a scatter plot. So, in educational researchers and vocabulary size of children as a function of age. Okay, so age, vocabulary size. How would you even count this? A scatter plot shows the direction of a relationship between the variables. A clear direction happens when there is either high values of one variable occurring with high values of the other variable, or low values of one occurring with low values of the other. So over here, there's clearly a direction. I mean, there can always also be an inverse direction going downwards. You can determine the strength of the relationship by looking at the scatter plot and seeing how close the points are to a line, a power function, an exponential function, or some other type of function. For a linear relationship, there is an exception. Consider a scatter plot where all the points fall on a horizontal line, providing a perfect fit. The horizontal line would in fact show no relationship. When you look at the scatter plot, you want to notice the overall pattern and any deviations from the pattern. The following scatter plot examples illustrate these concepts. So positive linear pattern, a very strong positive linear pattern with a one deviation. Okay, there's a pattern here, and then there's like one outlier. Negative linear pattern, a weak pattern, exponential growth pattern, and no pattern. Data really fit a straight line exactly. Usually, you must be satisfied with rough predictions. Typically, you have a set of data whose scatter plot appears to fit a straight line. This is called a line of best fit or least square lines. A random sample of 11 statistics students produced the following data where X is the third exam score out of 80. Y is the final exam score out of 200. Can you predict the final exam score of a random student if you know the third exam score? Yeah, so when you plot the data, it looks like this. So I mean, we can draw the line of best fit. Hold. Okay. The third exam score X is the independent variable, and the final exam score Y is the dependent variable. We will plot a regression line that best fits the data. If each of you were to fit a line by I, you would draw different lines. We can use what is called a least squares regression line to obtain the best fit. Consider the following diagram. Each point of data is of the form xy, and each point of the line of the best fit using the least squares linear regression has the form x y hat. Or y is the predicted line. Y is the predicted point. The y hat is read as y hat and is the estimated value of y. It is the value of y obtained using the regression line. So y naught, then y naught hat, x naught, y naught. The term sigma naught is called the error or residue. It is not an error in the sense of a mistake. The absolute value of the residue measures the vertical distance between the actual value and the estimated value of y. In other words, it measures the vertical distance between the actual data point and the predicted point on the line. Okay. If the observed data point lies above the line, the residual is positive, and the line underestimates the actual data value for y. If the observed data point lies below the line, the residual is negative. The line overestimates the actual data value for y. Wait, hold on. In the diagram in figure 12.10, sigma naught is the residual for the point shown. Here the point lies above the line and the residual is positive. Epsilon, okay. So over here the residual is positive. For each data point, you can calculate the residual of errors. sigma I. Okay. Each modulus sigma is a vertical distance. Okay. So we have some point. Let's draw pink. Let's draw a line of best fit. So there is a residual or an error between our predicted point, predicted and the actual value. So let's call this. What do we call this? Y hat is equal to mx plus c. So when we input x, we get some y hat value, which is not exactly the same as the actual value. So I call this x naught. This is sigma naught, and then I will 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 and 1, 2, 3, 4, 5. So sigma I is the actual value minus the predicted value. If this is truly the line of best fit, then sum of all the distances, sum of all of these sigma would be 0. But it's easier to do math with a square than a modulus. So when we square it, the negative goes away. But since this is the line of best fit, square of this, square of this, square of this, square of all of them, the sum of it should equal 0. This is called sum of squared errors. Using calculus, you can determine the values of A and B that makes SSE a minimum. When you make SSE a minimum, you have determined the points that are on the line of best fit. Turns out the line of best fit has the equation this. When A is this, B is calculated using this also. So let's say this over here is the average. This is the average. The line of best fit. So our first assumption is that the line of best fit will definitely cross the average. So you know what? Let's use B and A instead. So we have y naught equal to b x plus a. We know that the average values definitely are on the line. So we know that this is true as well. So average line, and we want to minimize this. Hold on, let me think about how I can do this. Um, line of best fit minus y. No, no, never mind. Let me see how I did this before. I wrote the derivation over here. So the loss is this. So hi is the predicted, xi. The loss is this. The loss is sorry, 0. We want to minimize the loss, right? Like we want it to be equal to 0. And instead of this, I will write I minus bx minus a is equal to 0, right? Then over here, b is equal to this. I should replace a with the mean value, maybe. So minus bx minus, so instead of a, I will write the average value of x. Sorry, no, minus this plus this. Yeah. So then it becomes, if I plug it in a, then it becomes plus b. Right? It becomes like this. Minus the average plus b equals 0. Is this correct so far? Now I can split them up. I have I plus, and b is a constant, right? Then I can make b the subject of the equation. Minus this upon this. I can multiply one of them with a negative, but that's not what they got. They got something else. Let me see where I went wrong. Oh, it is square. Never mind. All of this is wrong. Now let's see if I square it. Minus. So minus, right? Bx plus a square. Instead of a, I will write minus bx plus minus square. I will split them. Is this correct so far? We have the loss over here. We want the loss to a minimum, right? No, I think I have this wrong. If I sum the loss, I want the loss to be a minimum. And not zero. Zero is only for the zero is the only time it's zero is when this should be zero. If this is truly a line of best fit, this should be zero, but I made a mistake here. So derivating this with respect to xi, right? No, with respect to b. So this is what we are going to do. This line will be fixed, right? This line will be fixed at this point, and then we will just change the gradient. With different gradients, we would have different, like this value would be different. The sum of squared error, the SSE value. We want the value of the gradient that gives the minimum sum of squared error. So we derivate this with respect to b. If we do derivate it, we get 2. I will just take the 2 out. So 2, and then this becomes, I'm using the chain rule. Derivative 2 with respect to this entire thing would be all of this times it. Well, 2 will be inside. I just pushed it out. For the sake of simplicity, I will just put it in. Derivative of the outside times the derivative of the inside, which would just be this. And we want the minimum to be 0. But then 2, I can take it out. Divided by 0 is just 0. And then I have to make p the subject of this equation. So I can do that like so. Square. Then I can split the sum. Just do that. And then I can take the b out, right? Can take b out. And then I can rearrange to get b. This would be minus. Square. Since this is minus, I will just apply the minus to one of the value in here. Then I end up with this as the p value. Yep. A residual plot can be used to help determine if it can be used to help determine if a set xy data is linearly correlated. For each data point used to create the correlation line, a residue y minus y hat can be calculated, where y is the observed value of the response variable, y is the value predicted by the correlation line. Difference between these values is called a residue. A residue's plot shows the explanatory variable x on the horizontal axis and the residue for that value on the vertical axis. The residue's plot is often shown together with a scatter plot of the data. So, while a scatter plot of the data should resemble a straight line, a residue plot should appear random, with no pattern and no outlier. It should also show constant error variance, meaning the residues should not consistently increase as the explanatory variable x increases. Hold on, I'm thinking. Okay, never mind. A shop owner uses a straight line regression to estimate the number of ice cream cones that would be sold in a day based on the temperature at noon. The owner has data for a 2-year period and chose 9 days at random. Temperature and ice cream sold is following a strong correlation. This is the residual plot. Oh, I see. So if the data are close together, their residues would appear random, right? Their residues would appear random. But what if we try to plot a linear best fit on this graph and we try to make a residue, would the residue appear random? No, right? I'm thinking about that. Yeah, I think it would appear random because some points are really close, some points are really far. or no weight. While a scatter plot of the data should resemble a straight line, a residue plot should appear random, with no pattern or outlier. Should also show constant error variance, meaning the residues should not consistently increase as explanatory variable x increases. Least squares criteria for best fit. The process of fitting the best fit line is called linear regression. The idea behind finding the best fit line is based on the assumption that the data is scattered about a state line. Criteria for best fit line is that the sum of the squared errors is minimized, that is, made as small as possible. Any other line choose you might choose would have a higher SSE than the best fit line. The best fit line is called the least squares regression line. Third exam versus final exam example. The slope of the best fit line tells us how the dependent variable changes for every 1 unit increase on the independent variable on average. Besides looking at a scatter plot and seeing that a line seems reasonable, how can you tell if the line is a good predictor? Use the correlation coefficient as another indicator of the strength of the relationship between x and y. Correlation coefficient are developed by Carl Pearson the early 1900s as a numerical provides a measure of the strength and direction of the linear association between the independent variable x and the dependent variable y. It's calculated like this. Okay. Where n is the number of data points. If you suspect a linear relationship between x and y, then R can measure how strong the linear relationship is. Okay, I want to learn how to derive this as well. The value of R is always between -1 and +1. Size of the correlation R indicates the strength of the linear relationship. Values of R close to -1 or close to +1 indicate a stronger linear relationship between x and y. R is 0, there is no linear correlation. If R is 1, there is a perfect linear correlation. There is a perfect positive correlation. R is -1, there is a perfect negative correlation. Let me see what they are doing here. I have no clue. The variable R square is called the coefficient of determination and is the square of the correlation coefficient, but is usually stated as a percent rather than a decimal form. It has the interpretation in the context of the data. R square, when expressed as a percent, represents the percent of variation in the dependent variable that can be explained by variation in the independent variable x. R square presents percent of variation. 1 minus R square, when expressed as a percentage, represents the percent of variation in y that is not explained by variation in x using the regression line. So for the third final example, the linear best fit is this. R is 0.631, R square 0.4397. So approximately 44% of the variation in the final exam grades can be explained by variation in the grades of the third exam using the best fit linear regression line. Approximately 56 of the variation in the final exam cannot be explained by the variation in the grades on the third exam. Okay. And how much is it there? Um, okay, I'll try to finish this because I have to go somewhere after a while. The correlation coefficient R tells us about the strength and direction of the linear relationship between X and Y. However, the reliability of the linear model also depends on how many observed data points are in the sample. We need to take a look at both the value of the correlation coefficient R and the sample size N together. We perform a hypothesis test of the significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use to model the relationship in the population. Sample data are used to compute R correlation coefficient for the sample. If we had data for the entire population, we could find the population correlation coefficient. But because we only have sample data, we cannot calculate the population correlation coefficient. The sample correlation coefficient R is our estimate of the unknown population correlation coefficient. The symbol for the population correlation coefficient is rho, and R is the sample correlation coefficient. So R is known, rho is unknown. The hypothesis test lets us decide whether the value of rho is close to 0 or significantly different from 0. We decide this based on the sample. We decide this based on R and the sample size N. If the test concludes the correlation coefficient is significantly different from 0, we say that the correlation coefficient is significant. Conclusion: there is sufficient evidence to conclude that there is a significant linear relationship between X and Y because the correlation coefficient is significantly different from 0. If the test concludes that the correlation coefficient is not significantly different from 0, then the conclusion is there is insufficient evidence to conclude there is a significant linear relationship between X and Y because the correlation coefficient is not significantly different from 0. Performing the hypothesis test. Null hypothesis that rho is 0, alternative hypothesis that rho is not null. Significant linear relationship between X and Y. Null hypothesis, the population correlation coefficient is not significantly different from 0. There is not a significant linear relationship between X and Y in the population. Correlation coefficient being 0 means there is no correlation, right? This is the R value. Well, it's the rho value. There are two methods of making the decision. The two methods are equivalent and give the same result. Using the p-value, using a table of critical values. We will always use a significance level of 5%. Using a p-value. So, p-value is less than the significance level, you reject the null hypothesis, okay? P-value is calculated using a t-distribution with n minus 2 degrees of freedom. Formula for the test statistic is t is equal to r root n minus 2 over root 1 minus r squared. The value of the test statistic t is shown in the computer or calculator output along with the p-value. Test statistic t has the same size as the correlation coefficient r. Yeah, I mean that makes sense. P-value is the combined area in both tails. So t-value, use t-distribution. Yeah, I want to do an example. Using a table of critical values to make a decision. Um, the 95% critical values of sample correlation coefficient table can be used to give you a good idea of whether the computed value of R is significant or not. Compare R to the appropriate critical value in the table. If R is not between the positive and negative critical values, then the correlation coefficient is significant. R is significant, then you may want to use the line for prediction. Degrees of freedom n minus 2, then critical values. Then what are we saying? Whether the computed value of R is significant or not. Compare R to the appropriate critical value in the table. Okay, okay. The line of best fit is this, with R being 0.6631. There are 11 data points. So 11 minus 2 is 9. For 9, it's 0.602. So I think this R is fine, right? R is significant, reject the null hypothesis. So rejecting the null hypothesis says there is no correlation. Assumptions in testing the significance of the correlation coefficient. Testing the significance of the correlation coefficient requires that certain assumptions about the data are satisfied. The premise of this test is the data are a sample of observed points taken from a larger population. We have not examined the entire population because it is not possible to do so. We're examining the sample to draw a conclusion about whether the linear relationship that we see between x and y in the sample data provides strong evidence so that we can conclude that there is a linear relationship between x and y in the population. The linear line, the regression line equation that we calculate from the sample data gives the best fit line for our particular sample. We want to use this best fit line for the sample as an estimate for the best fit line for the population. Examining the scatter plot and testing the significance of this correlation coefficient helps us determine if it is appropriate to do this. The assumptions underlying the test of significance are the relationship between the variables being correlated should be linear. The data point should fall along this approximate straight line. The y values for any particular x value are normally distributed about a line. Okay, so we have the line of best fit, and the y values across the line are normally distributed. I see, I see. Assumption 1 implies that these normal distributions are centered on the line. The standard deviations of the population y values about the line are equal for each value of x. In other words, each of these normal distributions of y values have the same shape spread about the line. The residual errors are mutually independent. The data are produced from a well-designed random sample or randomized experiment. Okay. We call the third exam final exam example. We examined the scatter plot and showed that the correlation coefficient is significant. We found that the equation of the best fit line for the final exam grade as a function of the grade on the third exam. You can now use the least squares regression line for prediction. Suppose you want to estimate or predict the mean final exam score of statistics student who received 73 on the third exam. The exam score range from 65 to 75. Since 73 is between x values 65 and 75, substitute x is equal to 73, and then we get 179. We predict that the statistics student who earn a grade of 73, the third exam will earn a grade of 179 on the final exam on average. Also for 66 and 90, we just plug in the numbers here, right? Yeah, 90. They just plug in the numbers. The largest the final exam score can be is 200. The x values in the data are between 65 and 75. 90 is outside of the domain of the observed x values in the data. We cannot reliably predict the final exam score for the student. Understand really how unreliable the prediction is. Prediction can be outside of the observed x value observed in the data, make the substitution, then we get 126. Okay. Finally, outliers. In some data sets, there are values, observed data points called outliers. Outliers are observed data points that are far from the least squares line. They have large errors where the error or residue is a vertical distance from the line to the point. Outliers need to be examined closely, sometimes for some reason or another. They should not be included in the analysis of the data. It is possible that an outlier is the result of erroneous data. Other times, an outlier may hold valuable information about the population under study and should remain included in the data. The key is to examine carefully what causes a data point to be an outlier. Besides outlier, a sample may contain one or a few points that are called influential points. Influential points are observed data points that are far from the other observed data points in the horizontal direction. These points may have a big effect on the slope of the regression line. To begin to identify an influential point, you can remove it from the dataset and see if the slope of the regression line is changed significantly. Sample may contain one or a few points that are influential points. Influential points are far from the observed from other observed data points in the horizontal direction. So influential points are like far in the input. Outliers are like far in the output. We could guess at outliers by looking at a graph of a scatter plot and the best fit line. However, we would like some guidelines as to how far away a point needs to be in order to be considered an outlier. As a rough rule of thumb, we can flag any point that is located further than two standard deviations above or below the best fit line as an outlier. Against above or below the best fit line. You can do this visually in the scattered deviations above or below the best fit. Any data point that is outside of this extra pair of lines are flagged as potential outliers. So okay. So this here is an outlier. There is an outlier as an to a new line. There is one. Okay.